Şimdi kondaktörlere bakalım. Yine bizim bir medium'umuz olacak. Hatta işi biraz kolaylaştıralım. Vakum olsun, kondaktör olsun. Kondaktörde yine epsilon ve mu parametrelerimiz olacak. Bir de sigmamız var. Bir akım yaratacağız. Denklemlerimiz neler? Rho, normalde rho ama nötr olduğunu varsayalım şimdilik. Kondaktörümüz nötr, bir rho'muz yok. Elektrik alanın körlü eksi 1 bölü c dB bölü dt. Del dot b 0. Curl of h 1 bölü c j artı 1 bölü c de bölü dt. 4 pi bölü c. Ohm'uz law'umuz var. C eşittir sigma e. Bakalım. Önce in conductors'a bakalım da ondan sonra incident'ına bakarız. Dolayısıyla curl of h sigma e de bölü dt. Önce şuna bakalım. Elektrik alan nasıl bir denklem sağlıyor? Yani hatırlarsanız onu nereden çıkarmıştık? Curl of E denklemimiz vardı. Onun curl'ünü bir alalım. Eşittir eksi 1 bölü c d bölü dt. Curl of B'ydi. Curl of the electric field is the gradient of the divergence of E minus the Laplacian of E. This should be equal to minus 1 over c del by del t mu c, let's say del by del t, and the curl of B is 4 pi over c sigma E plus epsilon over c now there's okay del E by del t. Now this h is b over mu, so this is 1 over mu. So here we have mu over c, curl of B. Or divergence of E is equal to 0, because B is equal to 0 and D is epsilon times E. This is 0. So we end up having 1 over V squared del squared by del T squared minus the Laplacian of E. This should be equal to minus 4 pi mu sigma over c squared dE by dt. So if you just consider let's say the time derivatives. No, okay, so let's just look for a solution, a plane wave solution. A plane wave that is moving, let's say, in the z direction. E is equal to E0, e to the power I k times z minus omega t. If we just substitute it above, we get minus omega squared over v squared, and v is equal to c over square root of epsilon mu, plus k squared, this is the left hand side, this should be equal to minus 4 pi mu sigma over c squared. Well, the time derivative is minus I omega. So this is our dispersion relation. Now we can solve for k. K squared should be equal to omega squared n squared over c squared plus I 4 pi mu sigma over c squared times omega. So you see that k is a complex number. So we can write k as k1 plus I k2, ki being real numbers. And k1 squared minus k2 squared should be equal to omega squared n squared over c squared, and k1 times k2 is equal to 2 pi mu sigma over c squared. And what we have, our wave solution is E0, e to power I k1z minus omega t, e to power minus k2 times z. It is decaying as it is traveling. Well, k2 is minus 2 pi mu sigma over c squared k1 times z. So the larger the conductivity, the faster it decays. So even in electrodynamics, okay, one thing we see is that for a perfect conductor, there is no electric field in it, and hence there is no magnetic field in it, because sigma is infinite in a perfect conductor. There is no resistivity, so you cannot create any electric fields. There is what we call the skin depth. Well, let's see. For sufficiently small, now we can try to find a solution of K2, an analytical solution of K2 from here. The skin depth is defined as 1 over K2 This is the skin depth. This is how much the wave can penetrate into your metal. So is it? And we will now study what happens if you have an incident wave. You have your conductor, you send a wave into your conductor. Some of it will try to penetrate into, but as it's penetrating into, as it's propagating, it will just lose its energy. So it will just damp out. How much it can go before it damps sufficiently will be determined by this lambda parameter. The larger the lambda is, the more it can penetrate. Well, you see, K2 is kind of determined by sigma. It will be related with sigma. If sigma is small, then K2 will be small, and hence skin depth will be large. If sigma is large, then K2 will typically be large. If K2 is large, then the skin depth will be small. So the electromagnetic wave will not be able to penetrate. So what is K2? How can we determine the expression for K2, at least with some approximation? At least in sigma small limit, in that case, K2 will be small and K1 is typically omega n over c. This is our K1. And K2 will be 2 pi mu sigma over c times K1, which is omega n over c. C's will cancel. 2 pi mu over n times sigma over omega. And the skin depth will be somewhere around 2 pi mu over n omega over sigma. Yeah, n over 2 pi mu. Well, you see, omega over sigma, okay, omega actually is what we can control. We are sending the light wave, so we determine its oscillation. So as we change omega, larger omega has larger skin depth, which doesn't make sense. I would expect larger omega to have a, well, yeah, in a sense it makes sense. So larger omega will have a larger skin depth. So what is actually happening? You see, we are losing energy also. Electric field contains energy. So as the wave is propagating, it is losing energy. What happens to this energy? Remember, we are in a conductor, converting into heat. So we are losing energy because of the currents created. Well, if the frequency is large, you cannot really create a current. And we are assuming conductivity is small. That's another reason why we cannot really create a current. If we cannot create a current, we are not losing energy. But if omega is small, it's not really oscillating. So the electric field is pushing the charges in one direction for a long time. Eventually the charges start moving and they will dissipate energy. So in that sense, the small frequency will mean small skin depth, large frequency, large skin depth. Well, gamma rays, they basically go over anything. Such a large frequency. And omega is equal to 0 is the case when we have electrostatics. The skin depth is 0. So electric field cannot penetrate it. So that's what we had already seen in a conductor. In electrostatics, you cannot have electric fields. So this is in the small, when the conductivity is small. And if it's not so small, then you have to solve, you have these two equations to solve for K1 and K2 and determine the skin depth. Now let's get the reflection and refraction. Well, let me just look at the normal incidence. So there's no, yeah. this will be the easier case. So we have this electromagnetic wave arriving. This is K incident. This is, let's say, E incident. B is in which direction? This is B in. When it is reflected, we have this is K reflected, E reflected, B reflected, and we have K transmitted, E transmitted, B transmitted. Let's say this is Z, X, and Y. The electric fields will be E0 in the X direction. The B fields will be B0 in the Y direction. K is KZ in the Z direction. And of course, this K is imaginary when we are in the conductor. So K has both the real and the imaginary parts, and they satisfy these relations in the conductor. Then we have the continuity relations. K incident is this one, K reflected is minus KZ hat, and K transmitted is KT in the Z hat direction. KT is K1 plus I, K2, the real part and the imaginary part. This one. Why do you think it's similar? It decays. Well, okay, if you want to compare it, yes, in that sense they are similar. So if you remember the potential well problem, the wave function decays outside the potential well. Here in the conductor, the electric field decays. Now, by the way, before continuing, we have this phenomena. Furthermore, we have this equation tells me that K cross E should be equal to omega over C times B. For plane wave, this is always satisfied. It's just K, the magnitude of K is not necessarily omega over C in a medium. And again, keep in mind, we are talking about complex numbers over here. Since we are talking about complex numbers, the physical electric and magnetic fields are the real parts. So let's continue. The perpendicular is always 0 in this problem, so it's continuous. And B perpendicular is always 0 in this case, in normal incidence, so it is also continuous. Then we have E parallel is continuous, and H parallel is continuous. So these two are the equations that will determine me how much of it will be reflected, how much of it will be incident, etc. So let's see, E parallel is continuous. This just means E incident plus E reflected. This is equal to E transmitted. This is one condition we have. H parallel, which is B over mu, E parallel over mu, is continuous. So K cross, outside is vacuum, so K hat cross, or let me write it explicitly. B incident, the parallel B incident over mu, mu1. Let's say vacuum Outside we have vacuum, just for simplicity. Minus B reflected, again these are the magnitudes B reflected into. So I define B reflected as minus BR in the y hat. It is this minus over here. This should be equal to B transmitted over mu. Now B incident is equal to E incident. B reflected is equal to E reflected in terms of magnitudes. B transmitted is equal to N N times E transmitted. Now what is N? Now keep in mind N will have real and imaginary parts. Why? If you let's go back to our relation. You see, this is always satisfied. This relation. Well, let's just put K is equal to K in the Z hat direction, E is equal to E in the X hat direction. So K cross E is equal to K times E in the Y hat direction. This is equal to omega over C, B in the Y hat direction. So B is equal to K omega over C E. But K has a real and an imaginary part. So K omega over C is what we will call as N. So it has N1 plus I N2 in the metal. But you see, if N is a complex number, that means the electric field and the magnetic field have a relative phase difference. You see, in the case of the vacuum or dielectric media, we had the E and the B, they were in phase. They were either always in a maximum or always a minimum at the same time. But now, in the metal, there is a phase difference. They are shifted. So just substituting these into our continuity equation, B E in minus E R reflected should be equal to N times E, N over mu times E transmitted, which is N over mu times E transmitted is E in plus ER. So the reflected amplitude will be N over mu 1 minus N over mu divided by 1 plus N over mu E in, and E transmitted is 2 over 1 plus N over mu E incident. So they are basically not in phase. That the incident wave and the transmitted and the reflected wave will not be in phase. This is something new that didn't appear in non-conductors. Now, any questions? Basically, we are just repeating all the same things. So we just assume a solution, an incident solution. Some of it might be reflected. We assume a reflected solution. Some of it will be transmitted. We assume a transmitted solution. And then we just impose the boundary conditions on our interface to determine what is the reflected one and what is the transmitted one. Now, this is basically, as you said, the same thing that you do also in quantum physics. If you have a potential well or a potential step, let's say, you send a wave, some of it will be bounced back, some of it will be transmitted. You just impose the boundary conditions at the step, and that allows you to determine the reflection and the transmission coefficients. The same holds for these waves. Well, I wouldn't like to continue with this transmission and reflection thing. They're basically the same algebra over and over again. So, do you have any questions? You can also, for example, consider cases in which you have two slabs. Let's say you have a vacuum, and let's say glass. Now this is the typical case we have over here in the windows. So you can talk about normal incidence, which is the simpler one. You will have some wave incident. Some of it will be reflected. There will be, some of it will be transmitted. Let's call them ER. Those are the waves moving right ways towards the right. Well, this way, when it comes to the other interface, some of it, now it will be K prime. It will be bounced back minus K prime. Let me call them EL. And some of it will be transmitted, K, E transmitted. Well, of course, in this slab, you have the wave that arrives at the first interface. Some of it will be transmitted. And then after being transmitted, it will hit the second interface. Some of it will bounce back. And so you have all these waves bouncing back and forth. What I call ER is basically the sum of all these bouncing waves. And EL is again the sum of all these waves that bounce and move toward the left. And as they bounce from the left interface, some of it will be transmitted, and they will just keep moving towards the left. And this E reflected is the sum of all of them. So E reflected, in a sense, is formed by infinitely many reflections. Similarly as ER and EL, because they all have the same wave vector, they all have the same frequency, they all have the same polarization, the polarization in the same direction, etc. So that you can just sum them up and obtain a total amplitude. Then to calculate the reflection coefficient, the transmission coefficient, you just repeat everything we had done before. The parallel components and the perpendicular components of corresponding fields should be continuous across both of the interfaces. That gives you the equations that would allow you to determine all the unknowns. Basically, we have 4 unknowns here. We don't know E reflected, we don't know ER, we don't know EL, and we don't know ET, the transmitted. And at every interface, you get 2 solutions, 2 equations for 4 unknowns. You can solve them. Again, there's nothing new, just lengthy calculations. Well, the same thing. The only thing you have to pay attention to, if there's a conductor over here, then both ER and EL, they will also have a decaying profile. But the decaying profile... Sure, but I mean, you see, there are not many. I can sum all these infinitely many reflections, because all these right-moving ERs and the left-moving ELs, they will have the same decaying profile, just with a different amplitude. So I can just sum the amplitudes and just write one of them, and the amplitude will be just the sum. So ER, you're right, it will have a decaying profile, but there will be only one ER, which sums all these internal reflections. Again, nothing will basically change. Okay, so on Friday, we will start at radiation. So this is the medium. So how do we get, okay, once we have an electromagnetic wave, you can just study it, how it behaves at interfaces, etc. But how do we get that electromagnetic wave to start with? So that is what we will be looking at. By the way, some of these conditions, the continuity condition, etc., they are basically energy conservation. Some of them you can also derive by saying that the energy of the power of the incoming wave should be equal to the sum of the powers of the transmitted and the reflected waves. And the powers is given by the pointing vector. So that's basically another condition you can impose, but it will be basically this one. Of course, assuming you don't have any conductors. In conductors, you will get dissipation as it is traveling. Again, on the interface, you will get the conservation. Any questions? So what do we mean by a perfect mirror? No, it's basically a metal. You put a perfect metal. So you solve the same thing. K, E incident, K, E transmitted, minus K. Perfect metal is sigma goes to infinity. This is E equal to 0. Now, there is one problem here, though, if you set sigma goes to infinity. You see, we have this equation. And from this equation, we say that H parallel is continuous. But this tells me, this we can say, because we just take the integral of curl of H over some area. And then when you set the width of, if this is your interface, you take such an area. And when you set the width of that area to 0, then the E dot ds integral goes to 0. And D dot ds integral also goes to 0, assuming electric field is finite, etc. But if sigma is infinite, it's infinite times 0. So you cannot really use this condition. Or you can say that the electric field on the surface should be 0. That's another condition you have. Electric field on the surface should be 0. E is 0, so H parallel is continuous. That's basically the only way you can get out of this. You can satisfy this equation for a perfect mirror. Since sigma goes to infinity, if you want to satisfy this equation, E should be 0 on the surface and inside your metal. E is 0, and E should be continuous. So just outside, E should also be 0. So when you have a perfect reflection, E should change its direction. Okay. Other questions? So see you on Friday.